This last video I'd say is important just if you like physics, but I don't think it usually shows up in the AP test. But if you don't follow the derivation, totally okay. But you might want the end result in case one question on the multiple choice or the free response shows up. So you picture like a simple harmonic oscillator, something going back and forth. And let's say it's a mass on a spring. And the question arises is like, well, how much total energy does that object have? Mechanical energy, how much KE, how much PE does it have? Well, back from your days of energy, you'd say, well, like let's say you're picturing a mass on a spring, this oscillating back and forth. Well, whatever the mass is plus how fast it's going, 1/2 mv squared, that's its kinetic energy. Well, how far did you stretch it? And squared times the spring constant times 1/2. You could add that up. So the general form, if you're like, hey, find the total energy, you can figure it out just by taking kinetic plus potential. If you're good with that, you can keep watching, but that's a huge idea. Now here's the thing. we're going to derive an equation in terms of the things we were given. So we know what the velocity function looks like in terms of sine, and we know what the position function looks like in terms of cosine. So we're going to plug those in and get a specific formula that will help us calculate this. And if you're like, I'm good, we've learned a lot. But if you want to do it, it's actually kind of cool. So we say, hey, 1/2 m, but this is your velocity function that we derived from before. It's a omega sine of omega t plus v squared plus 1/2 kx. This is your position function squared. And right off the bat, I see a sine squared plus cosine squared, and I start thinking about trig identities. You know, cosine squared plus cosine squared equals 1. Recall, that's your x that we're using from, we derived in, I think, our first or second video there. And that's your velocity right there. So that's just what I plugged into our formulas. These are familiar. This is the new stuff, okay? The rest of it's just math. So we go through, we say, let's put that squared through. Let's put that squared through. And I always wrote the squared right there. I just like it better than the squared right there for my trig functions. So I want to get these speaking on the same terms. I'm like, that's got a Ka squared. That's got an Ma squared, omega squared. They look different. This isn't wrong. I'm just going to try to simplify things down with the knowledge I have. So look back, we know omega squared is K over M. You put that in there. And then you start seeing some things. You have an M on the bottom. Those go away. You have an A squared K. You have an A squared K. You have a 1/2. You have a 1/2. And all of a sudden you can start saying, well, I can factor out some things. So you factor out, both terms have a 1/2 A squared K, 1/2 A squared K. And so 1/2 A squared K. Then you get sine squared of stuff plus cosine squared of stuff. And that is just 1 because of trigonometry. Trig identities. You gotta love them. And then you're like, that's 1. So the energy total of a system, if you know the spring constant, and you know the amplitude you're bringing it back to, then you can find out what's the total numeric value of the energy total of the system. Because keep in mind, this can get less, this can get more, but the sum total of your energies is a constant value. Because let's say this was 3 joules and this was 7. This could be 5 and this could be 5. This could be 9 and that could be 1. But no matter what, the energy total will be the same. So the cool thing about this formula right here is that if you know the spring constant, you know how far back you pulled it to start, so you know what your initial amplitude is going to be there, then you can figure out what the total energy of the system is going forward. That doesn't tell you about the kinetic and potential at any given time, but it tells you what's the total, kind of, if you picture like fuel you put in your gas tank, what's the total energy you're dealing with. So there's a great diagram in our physics textbook, the survey book, page 460, figure 1510. It's a lot of information, but if you want to check it out, it's actually kind of cool. Okay, I can show it to you right here. Our physics textbook, page 460. Kind of neat, right? This is all things we talked about. So you have a mass on a spring. It talks about, you know, kinetics in blue, total energies in red, potentials in orange. So maybe you start off with all potential, and that's all your energy right there. They're equal. And all of a sudden here is all kinetic, and then they're equal. And then maybe later on you have a little kinetic, a little potential, but they still sum up the same total. And this is kind of a cool chart. I don't think you need to copy this chart down because if you have the notes, you'd be good to go. But it's just something to have on hand just in case. Well, that is the last video for simple harmonic motion, oscillators, and different things like that. And so thanks for watching, and I hope it makes a lot of sense. The first time you see it, it's kind of strange, but as you get working with the different formulas and things like that, you keep in mind the physical situation of potential converted over to kinetic. It actually is really cool stuff. So thanks for watching.